All right, last class we were struggling over this problem, so I think let's stop struggling and let's just punch through it and see what we can get. So what we're going to do is we're going to assume there's going to be an influx of students so that we're always going to be having students coming in and going out at the same amount. And so we're going to assume a lot of things that might not be practical, but the idea is that we still want to go by these percentages or these probabilities that they're creating here for the people that are going to become math majors or become not math majors. So not math majors means they're going to change their major to something else or graduate. So let's read through this again. Every year, 10% of the university students change their majors to math, and 25% of the university's math majors change to something else or graduate. So what we're going to do is we're going to establish a couple of different scenarios, and these scenarios are called states. And we are either math major or non-math. And by non-math, we mean other majors or graduating out of here. Okay? And we're going to represent these states as nodes or modules or vertices or whatever you want to call it. And then from here, we're going to take a look at possible transitions, and we're going to label the transitions with some probabilities. So, of the non-math majors, 10% will become math majors. And of the math majors, 25% will change into something else. Okay, so that means of these math majors who 25% change, what percentage of them don't change their majors? 75%. So 75% stay the same, and out of the non-math majors, how many of them stay non-math? Well, 10% of them change to math, and so the rest of them must stay to non-math. Stay away from math? So what we have here is transition state, and this is called, well, in setting this up, we're going to come up with a Markov chain. So we have two possibilities, math major and non-math major, and then at each stage, there's going to be some transition in changing things. So what we can do is represent this as a matrix of what's happening in the current state and what's going to be in the future state. And I think the current state can be looked at as the rows, and then what's happening in the future is a column. And so what we can do is we can identify the first column as the current math state to the non-math, math to non-math, and then we can label this. So from math to math is math to math is 75%, and from the current state of math change to non-math is 25%. Is that right? So current state math to future non-math is 25%. And then if you're non-math and stay non-math, that's 90%. And if you're non-math and you want to, whoops, try that again. If you're non-math, you want to become math, that's 10%. And then non-math to stay non-math is 90%. All right, so now that you have this information on these states, there's an interesting development here. If you notice, going from math to math or math to non-math, there's 75 and 25. That accounts for all the math majors and what happens to them and where they go. So one thing to note is that if you were to add up the columns, each column would add up to 100%, right? So the fact that you have a matrix whose columns add up to 100% means that this particular matrix is called a stochastic matrix. And a stochastic matrix is essentially a probability matrix that computes probabilities of how states change, how they assume that each column and each row represents a state and how they change over a period of however many transitions. This, by the way, is also known as, based on this Markov chain, it's also known as a transition matrix. So let's let P equal to this 0.75, 0.1, 0.25, 0.9, and let's call P a transition matrix. Okay, so for us, the word transition matrix or the phrase or the label transition matrix will be more important than saying stochastic. So let's just use transition matrix. All right, so the question is, if we start off with 13, 5 students and then 100 of them are math majors, what's going to happen in the long run? So let's try to figure that out. Is this okay so far? How this is looking? Well, last time I was kind of inviting people to tell me what they think, and so this time I don't care what you think. This is what we're going to do. Sometimes I care what you think. So. Okay. So now, what we're going to do is we're going to take a look at the transition from our original state where we have so many math majors and so many non-math majors, and we'll figure that out. So let's get a copy of our transition matrix. And let's take a look at what happens initially. So initial state, we have so many math majors and so many non-math majors. And I think initially we start off with 100 math majors, and if we're just counting the influx of incoming students, there was 13,500 total, and 100 of them became math majors, so we have 13,400 who are non-math majors. Okay, so what we can do, if we're not going to use a transition matrix, we can think out of the out of the 100 math majors, 25% of them 75% of them remain as math majors, right? And 25 of them become other majors. And out of the 13,400, 10% of them become math majors, and 90% of them stay as non-math majors. So we could do this calculation and try to figure out how many will end up being math majors after, let's say, after a year. And when I say we can do this calculation, I mean, can you do it for me, please? Yeah, well, yeah. Wait.
And the top one is 1415.
1415. Okay. So after 1 year, we would have. Now we went from 100 math majors to a whopping 1,415 math majors. That's kind of cool. Now I'm going to save some room here because I'm going to rewrite this equation into something that's hopefully a little bit simpler for us to manage. But now if I do that same process where I find out in my, so this is the end of my first year, at the end of the second year, I would take these numbers as these many math majors and non-math majors and go through the same sort of calculation, same sort of process, right? So out of 14, 15 math majors, 75% of them will remain math majors, and 25% of them will change to non-math. And out of 12,085 non-math majors, 10% of them will change to to math, and 90% of them will stay away from math. And then we could do the calculation for this to figure out what happens in our second year. Okay? Okay, so then after the end of the second year, this is what happens. Now, we can keep doing this, and I don't know if this reminds you of anything, but when you guys did compound interest, remember that? Ooh. So when you did compound interest, you couldn't just compute what happens all at once. You have to compute what happens at the end of the year so that you can compound that with a percentage of what you got at the end of that particular year. But eventually, the compound interest, you didn't have to do this, step by step, because if you wanted to figure out what happens in 50 years, that's going to take a long time, step by step. And so we came up with this formula. Do you remember what happened to the compound interest? What it eventually became? Something with E. Well, that's the continuous compounded. So if it wasn't quite continuously compounded, then it's still some number, but what did we end up doing to that number? Yeah, we kept on raising it to a power, right? We raise it to a power, raise it to a power. Now, interestingly enough, that's kind of like the same thing that's happening here. We have a state, we have a couple of states, and after one transition, they become, the states numbers change, and then another transition will take that current state and transition to a new state. And so we got all these number changes, and the way the states are going to change, it's going to end up looking like it should, hopefully, we'll see, end up looking like taking something to a power. Now, what I want us to do is I want us to think about this calculation, and this calculation and all the other future calculations we see have 0.75, 0.25, 0.1, and 0.9 associated with them. And it has two numbers that are repeated. So if you think backwards, this is just the matrix multiplication, right? Or one can think of it as a matrix being applied to a vector. Not yet. Well, we'll go there in a minute. But this is the matrix 0.75, 0.25, 0.1, and 0.9. That's essentially your P matrix. And this is being applied to the vector, initial state vector of 100 and 13, 4. And if you double check that, you do the matrix multiplication, the first row and the column vector is going to equal to this first calculation that we did. The second row and the column vector is going to equal to this calculation that we had already done. And then so your output then becomes the state. Where we had the results. And now if we look down at this next step, it looks like we're taking those same coefficients from the matrix but this time we're applying it to different numbers, right? And the different numbers that we got are 14, 15, 12,085. And if we do that matrix multiplication, we're going to get these two numbers again. And if we want to know what happens at the end of the third year, we would do the same thing, taking these two numbers and applying it to that matrix. So it looks like to get to the next state, we need to know what's happening in the current state. Does that make sense? Except for the current state. Yeah. But what? But is it really so dependent on the current state? Do we have to rely on computing the current state to go on? So think back to, again, the compound interest. If you're continuously compounding, or not even continuously, if you're compounding, then we got around to finding the current state. You know, if we want to know what happens in 50 years, we don't have to compute 49 computations to get to the 50th year. We just take advantage of the idea that this is being raised to a power of some sort. So how do we do that? Well, if we take a look at this, this value right here, that was equal to another matrix multiplication, wasn't it? So this thing is actually equal to 0.75, 0.1, 0.25, 0.9 applied to the initial state. And if we multiply that with what we're supposed to be multiplying it with, we have a matrix multiplication that is associative. And if it's associative, well, what if I decide, instead of applying this matrix, the multiplication with a column vector first and then matrix multiply the other one? Well, what if it's associative, then what if I take care of the two matrices first? And then I apply it to the initial vector. Then I don't have to depend on the current state to get to the next state. I just have to know what is happening in the initial. And if you remember compound interest, that's what happens. All we need to know is what happens in the first, your initial deposit, and then how many years are you going to compound. Okay? So that's kind of cool, you think? So at the end of the first year, well, the initial state gives us 100 math majors and 13,400 non-math majors. After the first year, we have 14, 15 math majors and 12,000 plus non-math majors. And after the second year, let's round up. got about 2,200 math majors and about 11,000 non-math majors. So what we can do is to figure out what happens in our third year and our fourth year, etc. We can carry on from here. Oh, well, I guess what I meant to say is, what if we wanted to know what happens in our fifth year? And the thing is that we don't have to figure out what happens in our third and fourth year anymore. We can just bypass that, because now we know that we're just going to take this matrix, the transition matrix, up to as many times as we need to get our state that we want to be in. So I guess the hard part here is multiplying, matrix multiplication. That's not so hard. So our transition matrix looks like it's 0.75, 0.1, 0.25, 0.9. So this is our transition matrix. Power, matrix, power. Whoops. So let me check your work. Make sure you did this correctly. So at the end of the second transition, that doesn't look right. No, because we took one away. Let's see.
Oh, is that the wrong kind of multiplication or something?
I don't think so.
Oh, there you go.
That's the first one. Oh. No. Yeah, so this is the first one, right? And if we square it, this is the stuff that I wanted to get. You're supposed to square it.
We got it, but didn't look like you counted P2 times 0 or something. Yeah. Looks like you counted P times 0 or something.
Well, that's how I got this one. But then if I had P2, which is supposed to be the P raised to the second power, I'm not getting let's just say P dot P. So power doesn't.
Power must be something else.
There must be a matrix power.
In Excel, do you use power or do you use exponent?
Oh, dealing with matrices with Excel is kind of tricky because you have to set up the
I mean, regardless of what big
Yeah.
matrix, like, if I want to raise 3 to the third, would I type in power 3 or X button?
Power.
Okay.
So matrix power is the code for this one. Matrix power P to the second. There it goes. Okay. So if I want to know what happens to the fifth or 5 times, then I would just do the matrix power to the fifth power and then apply that vector. Okay. What do you mean the long-term equilibrium?
Like if you raise it, you take the limit, the power goes to infinity.
You guys know what he's talking about?
I'd say after 100 years.
There's some balance that chemistry formula is still pretty much chemical reaction. Have an equilibrium and it helps stochastic.
So these guys are starting to talk about some equilibrium business, and the idea is that if you keep taking this to power and keep raising the power, eventually your output is going to start looking like it's going to settle into something. So let's take a look at that. And for that, I definitely want to use Mathematical. Let's see if I can get it set up. So, manipulate. Yeah.
Ooh, it's getting real.
I think your transitions probably won't go very far in terms of, you guys aren't going to have to raise things to the 10th power or anything like that. I hope not.
Otherwise, just to write the exact answer, like e to the fifth, but not actually.
All right. So this is the power for n. I guess I should go steps 1. So these are the states after. Do you guys understand what I'm doing? So I'm basically taking the matrix and raising it to a power and applying it to our initial value. So after the first year, these are the numbers we got. After the second year, we got 2270 and 11230. After the third year, fourth year, and fifth year, this is the one that we computed. We got 34, 21, and 10,000. 6th year, 7th year, and 8th year, 9th year, and then 10th year. Doesn't look like it's settling down. Let's go further to, let's say, 30. So as we take the powers higher and higher, you see something interesting happening here. Right? So what's happening is that if you just take a look at the top number as the number of math majors and the bottom number is the number of whatever non-math majors, over a long period of time, and these are the number of years that we're talking about, 9 years, 10 years, After 11 years, we have about 3,800 math majors and 9,600 non-math majors. And then it looks like over time, it starts to settle on 38,857 math majors and 9,642 non-math majors. So if the models are correct, which they're usually not, but the idea is that they make predictions based on this and they probably shouldn't go too far. But if the models were correct and accurate, then over a long period of time, the math department should be preparing for about 3,857 math majors in their department every year. Okay, so you know that's never going to happen, but that's the idea behind forecasting here. You're making predictions. So if you just take a look at a couple of consecutive years, like between 20 years and 21 years, that's when you see the numbers settling down to an equilibrium.
So for a 2 by 2 like that, does it always reach equilibrium no matter what the number is?
It has to be yes, it has to be, but it has to be a stochastic matrix.
And is that true for bigger than 2 by 2?
Yes. So if you had 3 by 3, 5 by 5, 10 by 10 matrices, as long as the columns add up to 1, you got a stochastic matrix. Doesn't matter what the starting point is, you're going to end up with this. Okay? Oh yeah, yeah. So that's another piece of information, that each resulting computation of the Markov matrix, we didn't do this, but you should multiply, we should square this matrix. Actually, I can do it real quick. No. Probably not. If you look at something raised to the second power like this, the matrix, the stochastic matrix raised to the second power, if you look at this result and you look at the columns, you can kind of do it in your head. If you approximate enough, the columns are all going to equal a 1. And so if you keep doing that, to the 100th power, for example, a stochastic matrix raised to any power is still going to be a stochastic matrix. No. Yeah. All right. Okay, so how do we want to say this little fact over here? What? Well, let's find a conclusion for our problem first. This is the problem that we start off with. So in the long run, and in this case, this is 20 years that we've calculated our results here. In the long run, there will be 3,856, let's call it 57, math majors, and 9,643 non-math. Okay? And we see that it doesn't change after that either, right? So the values don't change. So years past 21, values won't change. Okay? Is that cool?
So move it to 30, must be.
Well,
Oh, that's not right.
yeah, so that's going to be our next next thing that we're going to look at. No, actually, it'll be a little bit more interesting than that. So this is what happens in 30 years compared to what we had 21 years. You'll see that it remains constant. All right? Good? So now the next question is, what happens to the matrix? What's happening to the matrices? If we're multiplying it by the same number, by 100, comma, whatever, if we're multiplying it by that, then that means the matrices that are being raised to the power, there's something interesting happening to that as well. You think? Yes. So let's try to figure out what's happening to those matrices. So instead of looking at the let's copy this whole thing. Oops. We don't want 0, we want to start with 1. So let's look at the matrix now. This is our transition matrix, P, right, the original one. If we raise it to the second power, we get this matrix. And then if we raise it to the third, fourth, fifth, sixth, etc. So if we raise it, let's see, let's stop somewhere over here, 11th, 12th, we get 28, 28, 13. So what do you think is happening? The rows look like they're becoming identical, right? Or the columns. Well, it depends on how you look at it. The entries in the rows are identical, which makes the columns identical. However you want to look at it. There's flexible interpretation there. All right. So I'm letting you guys go again. So stop. Right? What happened last time? I let you guys go, and then we just kind of went on tangents and tangents. Yeah, after this example. We'll have, I'll say about 15 minutes for the test. So the idea is that in the long run, independent of the initial state, if we're not dealing with states, if we're looking at stochastic matrices, if you're taking a stochastic matrix and raising it to a power, in the long run, your columns, your entries in a row will be the same, which makes your columns identical. Okay? The entries in the rows will be the same, which is going to make your columns identical. The entries in the entries in each row will be identical, which makes your columns the same. I can say that 5 more times. But the idea is I hope you know what I'm talking about. So, just looking at the matrix, So your transition matrix, which I think we called P, raised to the nth power, settles down into a matrix with identical columns. So this becomes about 0.28, 0.28, 0.7, let's call it 0.29 so that I can keep 0.71, because it needs to add up to 1, right, approximately. So 0.29, 0.29, 0.71, 0.71. So it becomes your transition matrix has this steady state or steady transition over the long run. Does that look like a 9? Looks like a bunch of scribble. So that means now we can have any initial state that we want to deal with and then apply it to this matrix to see what happens in the long run. So say we didn't start off with 100 math majors and et cetera. So we start off with something different. Then we can come up with something in the long run. Okay? So does this make sense?
This is what that example was doing before class with the example.
Yeah. So this is just finding their steady state matrix. Okay. Now, what this is telling us is that in the end, you got 29% and 71%. In the long run, 29% will eventually become math majors, and 71% will eventually become non-math majors. Does that make sense? So what's interesting about this is that if we just look at the percentage, this is going to be our steady state. Right? So what? So if we take our original vector, or original transition matrix, this is, let's see if this will work out. And then apply this to our steady state. Before we do this, before you do it, what do you think is going to happen? Take a, which one? The total number of each one? It's a steady state. The transition, well, let's just do it. What's 0.25 times 0.29 plus 0.1 times 0.71? Yeah, really? What is it? You guys should try it too. Well, 0.25 times 0.29 plus 0.1 times 0.71. Oh, really? That wasn't what I was expecting. What is it? 0.1? 435. Oh.
And yet the other one is 0.8565.
Why were you surprised?
I was expecting 0.29.
Well, me too. 0.75.
Oh. Yeah, thanks, Rita. You see what I did wrong? Now that the punchlines. I gave you guys the wrong matrix. Whoops. All right, now let's try it. Now you should get 0.29 for the first one.
0.29. So I'm going to bet you second one. That's what I thought you would get.
Yeah.
We're always multiplying it by, and so this is steady state.
So this steady state, I think it's sometimes called a steady state vector. So whatever the initial condition is. And your steady state vector tells you the probabilities that you will land in a particular state. So we got 29% probability that the portion, or 29% of the people that are in the school will eventually become math majors, and 71% will become non-math majors. So again, that's a little too high, I think, but that's what the problem says. And so what's interesting about this is that in this particular case, we can collapse our transition matrix as the powers go off to infinity. We can collapse that to just a vector, since the columns are the same. We can just look at the column vector and call that the steady state vector, and that's what's going to happen. Wait, one more thing. So another interesting fact about this steady state vector is that if we call this our p's and x's again, for a stochastic matrix, it turns out that there's going to be a special vector x, so that p times x is going to equal to that vector x. Right? So this is your p, this is your x, this is your x, and there's a special vector x. In this case, it's 0.29, 0.71. That's going to be equal to this. So this is a special property for stochastic matrices, but we'll see in the future that there's going to be a similar property for any matrix that we deal with, or at least any invertible matrix that we deal with that has this special vector. And what you could do is you could play around with more matrix algebra here. Oops, I put an arrow on the p. P is a matrix, this is a vector, and if we multiply this by the identity matrix, and bring it all to the other side, we can take advantage of some distributive properties . We can take advantage of some distributive properties where we can easily find this. We can easily find this the steady state vector now, without having to take this vector to a power, to larger and larger powers. Do you see this? So this would be your way to find the steady state vector. I hope so. Okay? So you'll be responsible for finding the steady state vector, and since you don't get to use Mathematica and take the power up to like 30 or 40 or 50 times, you just have to find it this way. All right. We have about 10 minutes to talk about the test. So yeah, if you want to finish this idea, take our matrix P, subtract it from the identity, or subtract the identity matrix from that, and then solve for X. And then if this is a homogeneous system of linear equations, so solve for X, and then when you find your X, you should get about 29 and 71. Okay. All right. We have a test a week from today, but our next class time is a holiday. We don't meet. And so we're going to have a 10-minute review. I will try to find something for you guys to do online.
Can you give us an outline?
All right. So your test will be on chapter 3. Just chapter 3. All right. So this 100-point test will be broken up to a 20-point portion online. This will be 10 true-false questions. Each will be worth 2 points that you'll have to do in web access, and I'm still working that out into something that hopefully you can read, because when I translate things in web access, I try to make it look mathy. I have to go through the LaTeX form of things, and sometimes it gets weird. So hopefully I get that figured out, and you will get to do a true-false portion that you'll get 3 attempts on online. That'll be worth 20 points. 2 points for each question, yeah. 3 attempts. Oh, no, it'll be, I will have a bank of 20, 30, or 40 questions, and then it'll automatically select 10 questions. And so in your next attempt, you maybe I should give you 2 chances. No, I meant 2 attempts. So let's put it this way: if I can dig up 40 questions, then I'll give you 3 attempts. If I can't dig up 40 questions, true false questions, then I'll give you 2 attempts. So 2 attempts, true false. No, it still needs to be a combination. Sergio?
That's attempt per question, not per quiz, right? Or
I think it's per quiz.
per quiz?
Yeah, so you have to fill out all the quiz, hit submit, and then if you want to take another attempt, it'll dig up 10 new questions,
But
and
that
then
would be like 1 attempt per question.
no, 1 attempt per quiz. 2 quiz attempts.
Okay.
So you can't do it problem by problem. You have to do the whole quiz. Yeah. I don't know yet. It'll probably, so the in-class, we'll have the in-class on Wednesday. It'll probably be due that evening. Yeah. I don't know. I hope so. Yeah.
So you take the test attempt, does it tell you like a score?
Yes.
Does it tell you
So when you take one test attempt, it'll tell you the score. You can review it, see what you got wrong and what you got right. And then when you do the next attempt, it'll shuffle the problems. It'll dig out more different problems, and then you'll have a new set of 10 questions. Maybe not all new. Maybe 1 or 2 are going to be the same, and then you go on from there. I don't know.
or a best of your 2 attempts?
Yeah, it'll score the highest of the 2 attempts. Okay. Okay.
Well, if you got a 10, you would
Yeah.
Then we'll
I don't know. We'll see. Yeah, so probably no calculator. For the proctored portion, you will have 4 problems. Problem number 1 will ask you to decompose a matrix to an LU or a PTLU, or both. The next one will give you a matrix, and it'll ask you to find the row space, the column space, and null space. It'll probably ask you to find the basis for each of those spaces and the dimension. The third one, we'll take a look at matrix transformations. We're going to stick with linear transformations. So what we're going to do there is you're going to be given, describe maybe, you're going to be asked to find a matrix that represents a particular linear transformation, or maybe you'll be asked 2 of those, and then you'll be asked to compose them, and then you'll be asked to take like a square or a figure, and then apply those matrix transformations to that figure to see what your resulting figure will be. So in class we had a square with different color circles on the edges, and then we saw what happens after matrix transformations. So you'll be asked something similar to that. Email me. So Becca's going to email me. If she forgets, then I won't do it. But when she emails me, I will be reminded to post the graphing calculator program that I had, where I just change the matrix and then you see what happens to the transformations. You need graphing calculator, so it's going to help if you. No.
We want scientific calculators. It's like Fisher Price calculator.
Okay. Well, the thing is, the matrices that I'm going to give you will, for the Markov chain, for example, I'm going to stick with a 2x2 matrix. So it's not going to be, the hardest calculations you'll have to do is like 0.75 times 0.1 or something like that. So I would say let's just not worry about having any calculators. And if you need to know what 0.9 and 0.75 is, you can come up and ask me, and I'll punch it into my calculator and tell you. Okay. All right. So that's transformations. There will be no proofs for this test.
Can we bring a
Maybe for the final. Oh yeah. So you get to have a sheet of notes, whatever you want to put in there. So the Markov chain will be similar to the problem that we have. I will address things like what's your steady state vector, what's your transition matrix, what's your initial state, what's your state in 2 years. I probably won't go more than 2 years because you'll have to square your matrix and apply it to that. Which kind of leads me to the homework. Homework 3.7 has 2 problems that has Markov chains, and then beyond that are problems that we didn't go over. How many people started the 3.7 homework? Okay, so I was just going to knock that out. I mean, not count it as part of your grade.
Can you leave it there?
Why can't I do it though?
Yeah, so I'll leave it there. What?
Extra credit if we do it.
No.
20 points.
I thought about it, but no extra credit. I'll think harder. I'll think some more about it. But here's the deal. So I will not incorporate 3.7 as part of your homework scores. However, the first 2 problems are probably important problems for you to try to do and understand to prepare for the last question on this test. Okay? Say it again? So the homework 3.7 is not going to be part of your grade, but the first two problems in that homework set will tie into what we're going to do on the test. All right? I will leave it up. Say it again? I will try to post a study guide by Friday. So tomorrow, some of you guys are in this class again in the differential equations, so just remind me to put a study guide. What? No. All right. See you guys. Have a good, for those people who I won't see, have a good weekend.
Do you have
Yep.
makeup for this test?